Well, at the end of class last time, we were looking at this family database, and we had this example of Tom Fox and Ann Fox and Pat and Jim were the kids. And so we're going to pick up right where we left off there. And let me just say a word about the homework. There is a homework assignment due tonight, right? And I think, did you guys have some questions about, you probably had some questions about the finite state machine. Maybe some of you did. Did you? Actually, because I think some of you have not taken some of you are taking the things a little bit out of sequence. How many people here have had, I don't remember now, it's foggy in my mind. How many people here have not had computer systems? Just about everybody but 3, yeah. So anyway, actually the assignment is really, really easy. There's a cookbook way to do it, and I think you'll see when we get through chapter 4 today. At the end of chapter 4, I think you'll see that it's very simple. So I think we can go ahead and have it still be due tonight, and it won't be a problem. I think this is this is kind of a breather chapter where things aren't really that difficult to get. Okay, so let's start where we left off last time, and we'll go to our demo. Okay, so here's our demo. Now, I think at the end of class last time, according to my notes, we did what did we do? We did husband, right? And we did wife. Do you remember that? Hello? Okay, so is this microphone on? And then, did we do all the employed wives? I think we did. Yeah, we did the unemployed wives, and yeah, we did that. And then we did child, right? And then I think we did child X, if, family, any mother, any father, any father, any mother in that order, and then children, and then capital CH children in this example would be instantiated to a list, right? And then we use the member, which works on a list, okay? And so we queried all the children, and we also queried all the people. Do you remember what would happen? Do you remember what happened if we tried person X? What was the problem with person X? Do you remember what happened if we said person X?
It didn't work.
Why didn't it work? This is actually an interesting question. Because yeah, person is like inside a family, and we don't have any facts up here in our database for person, right? So how did we solve that? Do you remember how we solved that? Exists. So we said exists person if what? If, well, but what kind of persons are, I mean, can't we use something that we did before? What kind of persons are there? There's only 3 kinds of persons, either what? Yeah, either husband or wife or child. Okay, so exists person if husband person or wife person or child person, right? And so, and I think if we query all the people, it's exists P, right? Let's try that, make sure that works. I think that's where we ended. Exists P, and sure enough, and what gets returned with exists P? What are these things that gets? This is an important little point. What gets returned? A person, and what is a person? It's this, it's a functor person, and then how many arguments does person have? Let's see, Tom, Fox, date, and works. How many arguments does person have? 4, and so there they are. Person, 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 person. All of them have 4, right? Is everybody good? Whoops. Okay, let's continue this madness. how would we get the names? Now, one of the things you have to do for tonight is you have to write queries. You have to, in your homework assignment, I gave you instructions on how to do that on the web page, right? About how to include that in the documents section so that I can copy and paste to do your queries. So now, how do we query how do we get the names of all the people in the database? So, oh, I just gave it away. We'd say, we say exists person. Okay, because what does exists do? When we say exists P, down here when we said exists P, what did we get?
If the person is either husband, wife, or child.
Right, it returns all of these, and then what will happen? I mean, how will the matching happen?
It'll return their first and last name.
Yes, and these can be anything, right? Okay. So let's try it. Let's try this query. Now I've written them all out here so I can copy paste. Okay. So look, name Tom, surname Fox, and what happens if I check another one? Name Ann, surname Fox. Name Pat, surname Fox. Name Jim, surname Fox. Does everybody see how that query worked? Okay, so that's how you would query the names of all the people in the database. Now, how about birth date? What we want is date of birth. Well, let's write date of birth PD. So what's the arity of date of birth here? 2, so it's date of birth PD. D is the date of birth of person P. So here is our fact for date of birth. So notice that this is not commented. So when we consulted date of birth, this is date of birth. So now look. What does date of birth take as its first argument? It takes a what? A person, right? And what kind of person does it take? It takes a person, any what? First name, any surname, and then a variable for what? The birth date, and then any what? What was this one? Employment status, all right? So, and then this date is this date. Are you with me? Okay. So how would we with that as the date of birth? How would we query all the children born in 1983? Well, see, that's a good question. The reason that won't work is because P. What's P? A person. So how would you get? You have to see. And now here's the key to doing these problems. You have to get a variable to be instantiated to a person, and then comma, and then once that's instantiated to a person, then you can use the date of birth. So the query would be child X. Do you see why you can't do person? Because when you say child, because look, what happened when we did child X? See here, if we do child X, here, what do we get? We get this person, and then we get this person on the next go around. Are you with me? So therefore, so what do? We do child X. The first time child X executes, X is instantiated to what? This person, right? And then that X is instantiated. That person is what's here, which goes to date of birth. Are you with me? So therefore, let's try this query. Okay, so we'll copy this. So check this out. And what happens? There it is. That person is the child born in 1983. And is there more? Oh, were they twins? Oh, I think they were. Interesting. They were born on the same day. Does everybody see how that query, how you have to use that query? You got to be careful of that P thing, you know, you got to have a, is everybody with me on that? Okay. How about the birth date of Tom Fox? How would you query the birth date of Tom Fox? So that first query is a query of all the children born in 1983. How would you query the birth date of Tom Fox? Somehow you got to have what? Yeah, but P, how are you going to get P to be instantiated to one by one to all the people in the database? How are you going to do that? Say it again? Yeah. So what would you say? So if you remember what happened when we did exists P? Remember that? Exists P. If we do exists P, what does that give us? Boom, 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 boom. You know, all of them. So therefore, what do we need to do here? Exists X or P or whatever, yeah. And then what? Now we got to get it to do what? We got it. Only the person who's what? Is. Now is does mathematical computation, so that's not quite right. Are you with me? What? No. That's not, you're using all this fancy later stuff. What was the very first operation we did? Huh? Match. Yes, match. Because when it matches, you know, it succeeds or not, depending on if the match happens. So what would it be? Now, person, yeah, and then what? And then Tom, comma, Fox, yes, Tom, yeah. And then anything, those anonymous variables, right? Anything, right? But what do we want? We want the birth date. Well, no, not date of birth, because what were the parameters of the...
Well, you would add the first name.
Oh, I see, and then you could do the date of birth of that person. Oh, yeah, yeah, actually, that's what it is what you would do, date of birth of person. So exists P will get all of these, and then P match person Tom Fox will just get us this one, and that will be, and so at that point, P will be that person, and then we can use date of birth PD. So let's see if that works. Does it? Copy, paste, and check it out. Yeah, and not only did it give us the date, it gave us the instantiation for P to make sure that that was Tom Fox, and nobody else is instantiated to that. Is everybody? Are we getting the hang of this now? Okay. How about the salary of a working person? Which field of the person was that? The last one. So salary PS. So now let's salary PS. How do we write? S is the salary of person P. But remember, what was that fourth one? It was either. What was it? It was either works or unemployed? Okay. So how do we do that? Two facts. Salary, person. Is everybody with me on this? This has been this is a rule. It's actually a fact in our database. Yeah. And what it says is that salary. When will salary succeed? Yeah. When works matches the fourth one. Any first name, any last name, any what was this? Birth date. And then this works has to match the works, you know, the works functor. And what was this? Where he worked, where the person worked. And then that was the salary S. And then if that S is this S, that's what the salary is. But that's if there works. Now we need another fact. Because it says 0 if unemployed. So now what? See, that's what if this matches works. But then what?
And then the same thing, and this is unemployed.
Unemployed here will be 0, yes. Now, does everybody see how that worked? Okay. Yeah. Well, this is a rule, this is a fact that tells us when salary will succeed. Do you see what I mean? So whenever the salary is a goal, it will go through and it will see this salary, it will go to this fact, salary, and salary, the goal, if the salary goals match, if the functors match, if salary matches, then it will look and see if this matches person. Are you with me? Because by the unification, then we'll see if this matches person, and then it doesn't matter, and then it will see if this matches what? Works. Yeah, if that matches works, and then anything, and then it will instantiate S to this. Yeah, and then it will see if that matches this, and if so this will be instantiated to the salary, and then this S will unify to that. Will be instantiated to that, and that's what will get reported. And similarly for the unemployed. Well, we have to put that in our query. You see what I mean? So look, so here's the query. So let's do one. What is the query of the salary? What is the salary of Tom Fox? How would we query that? So think about how would we query Tom? How do we do the birth date of Tom Fox? Exists P, and then what? P is person, Tom Fox, blah blah blah, and then what? Salary P, yes. Yeah. Does everybody see the pattern now? So your question was, where did that person come from? And the answer is it's part of the query. I mean, you have to set up your query so that it's instantiated. So here, let's take a look and see if this gives us. Well, what do you know? Tom Fox made $15,200 working at BBC. Yeah? Is everybody good? Okay. How about the salary of Ann Fox? Do you remember remember Ann Fox? Was unemployed, right? So just to show you that this does return 0 for an unemployed person. There's 0, and there's no more solutions because there's no more Ann Fox in the database, right? And how about the names? Now here comes one that's similar to a homework problem exercise. How about the names of all the unemployed people born before 1973? Now here you kind of have to string them along. So what's the first thing? First of all, it's obviously going to start with what? Exists. So it's going to be exists. Oh well, shoot, have it all on one line. So exists what? And then person, and then name and surname is going to match with all the people, right? For whom person, but only those for which what? There is date, arbitrary day, arbitrary month, and then year, and then for work matches unemployed. At this point, what will happen? If it succeeds this one, then now it's comma, so now what? Year will be instantiated to the year of the person who is unemployed, and then comma what? Year less than 1973. Do you see how year got instantiated here? This is comma. No, see, this goal right here is outside this goal, and it's the comma, and it goes from left to right. So does everybody see how that works? This left to right gets the year instantiated to the year. Oops, I forgot to copy. Okay, so let's do copy. Down here we'll do, and it will show name and surname Fox, year 1961. Is anybody else? No, nobody else.
So since you weren't looking for a specific person, that's why you didn't have to do exist P match a person.
In fact, we want the first goal to match for all people.
Yeah.
We want the first goal to match for all people, and then the second goal is the one that only succeeds. So the first goal will succeed for all the people in the database.
For all the unemployed people.
Sorry, you're right. Not all the people. All the unemployed people in the database.
So like
And then the second goal will fail for those that have a year greater than or equal to 1973.
So like the first goal is saying like it's gonna give you all the people who exist who are unemployed.
Yes. Yes. And do you see how it does that with the matching? Yeah.
Could you have done it using like exists P and then P equals person blank blank?
Actually, you could have, actually, that's a good point.
I tried
You,
that.
and it didn't work? You should be able,
Unless I typed it in wrong, but
yeah, the question is, could you say exists P, comma, and then what? P match,
Yeah.
did you say P match?
Yeah.
And then P match person?
Blank 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 and then
Oh, no, well, if you do blank blank, then we won't get the names instantiated.
Name, surname.
Surname, yeah.
Blank, unemployed.
No, because you need the year.
Oh.
We're trying, the whole idea here is to get
Oh,
the,
okay.
is to
So
get
then
the
you
year,
choose Name, surname, year,
comma,
comma,
unemployed,
and then year less than.
and yes, I think you should be able to do it that way. I don't want to take the time to try it here, but I think that should work. Did you try that and you couldn't get it to work?
I did, and it didn't work unless I also typed it wrong.
I would think that it would work. I think that approach, seems to me like that approach should work. I've been bitten by Prolog so many times. It's a kind of a strange thing. You kind of have to have the Prolog interpreter right there, and I mean the search engine right there, and try stuff out sometimes. Sometimes unexpected things happen. Can you not get it to work that way?
I keep finding like mistakes.
Oh, and what you type? Okay. Well, anyway, let's examine that offline.
Yeah.
Okay, how about this one? Query, people born before 1970 whose salary is less than $8,000. So now, what do you think, sports fans? Yes, and work, and then, yeah, good, with unemployed,
Less than 8,000.
yes, but then also the year.
Oh, yeah.
So then so we'll do both of those one after the other. Are you with me? So let's see so first of all, exists person, we'll do this on separate lines. So exists person, and now what? And this is capital P person, so P is a variable. And so now what? Actually, isn't this doing it the way you asked to do it? Exist P? Didn't you say to start with exist P? I think this is what you asked on the previous query. Can we do it this way? Yeah, we're going to do it this way. We're going to do it your way this time. Okay, so exist person, comma. Ah, good, it worked. Ah, good. You had to get it all typed in right. Yeah, you're right. Yeah, they're long. That's why, you see why I'm doing cut and paste here, or copy and paste. Okay, so exist person. Now what? Now what do we filter? Now what do we get from the person? Well, how about date of birth? Because date of birth requires a person for the first argument, right? And then the date as the second one. So you see date, and now what will year be instantiated to in order for that match to take place? It will be instantiated to the year, the birth year of person, right? But now what else do we have to check?
Before 1970.
Right, so we'll check the year as less than 1970, and if it passes this, then we'll go on, otherwise it'll fail, okay? But then what do we have to do? Salary, so now what do we do? Salary, person,
Person.
capital S, salary, and now what will we, now capital S salary will be instantiated to the salary, and now what?
Salary less than
8,000. Right. Now, we're going to have to do this. So first we'll do celery. Eating celery sticks. Okay, so first we'll do exists person, and then we'll do date of birth person, blah, blah, blah. And then we'll do, sometimes I'm copying the line feed and sometimes I'm not. year less than 1970, and then we'll do comma, right? So then we'll do salary, and by the way, who satisfies all of this stuff? I tried to make it so that we would get at least one success for each one of these. Did this satisfy our query? Person and Fox, unemployed, 19, yeah. And I think there's no one else who satisfies that. Okay, what now? So you guys starting to get the hang of how to do this? How about the names of families with at least 2 children? Okay.
Well, I guess,
Well, but now, how do we know how many children? At least 2.
Because the third parameter of families is.
The Yes, good observation. The third parameter of family is a list. So how do we? It is a list. So what matches? Check it out. Look at this. Is this slick? Family, person, and then name, right? And then what? The list of children matches what? At least 2 in the car part, right? In the first part. At least 2 in the first part, and any number in the second part of the list. Yeah? So just to show you, check this out. And sure enough, the Foxes have 2 children. Okay? And so they satisfy that criterion. And now, how about total? Now, here's what we want. We want the total we want the sum of all, we want to, for total, we want to give a list of people, and then what we want is the sum of their salaries is the sum of all the salaries in the list of people. So if the list is empty, what's the total of all the salaries of a list of no people? It's 0. So does everybody see that that's our base case? Otherwise, what do we have? Now check this out. Otherwise, what do we have? Total what? A person, and so person for the first part and list for the rest, yeah. Sum if what? Now's your chance to use your is. Because what does is do? It forces the what? The arithmetic. Yeah. So now what? If what?
total list, that's 1.
Yeah. Well, if we do salary person, we know person is an individual person, and so we can do salary person S, and so now S is instantiated to the salary of the first person. But now what do we do?
Sum is S plus.
Yeah, plus what? If you say sum is S plus, the question is plus what? So what do you have to do first? Yeah, you have to total what? The list, yes. So you have to total list, rest, and rest. Oh,
Is it sum?
rest is the sum of the rest. Yeah, I would have been better to call this sum of rest. But anyway, this is from the book. But whatever. Okay, so rest. Now what?
Sum is
Is-
S plus 1.
Yes. Yes. Good. So how do you get the total income of each family? Check it out. Family. So we have family, husband, wife, children. Now when we say family, husband, wife, children, husband is initiated to a person, wife is initiated, is instantiated. Let me say this again. Husband is instantiated to a person, wife is instantiated to a person, but children is instantiated to a what? To a list. So what do we have to do? we have to provide total with a list, right? So what is the list that we provide to total? The list that consists of the husband and the wife, and the cooter is the children. And then income is the income. Amazing. Actually, I need to demo this. Oh, say that again? The 2 children?
Yeah, because in family, isn't like the first slot husband, the second slot wife, and the third slot the list of kids?
Yes, and so what this is doing is, this is instantiating name to the surname of the husband,
Okay.
and then anything. Yeah, are we good?
Yeah.
Okay, now actually, I should demo this before I kind of jumped ahead here. So let's get the total income of each family. Here, let's demo this. So here's family, so we'll do this. Family, husband, wife, children. And then we'll say total, let's see how this works. And then we'll do total husband, wife, children, income. And now, you want to guess what happens here? What gets instantiated to what? What variables do we have? Husband, wife, children, and income. So what will it be for our little database? It would be person, Tom Fox, right? And then the wife will be, yeah, and then children will be the list of the 2 children, and then, yeah, so there it is. Children is the list of the 2 children. Husband is that person. Income kind of came out in the middle here. Oh, is that how it is?
Yeah.
CHIW. Oh, yeah. Oh, good point. Nice observation. And then are there any more? See, so if I press semicolon, there's no more in our database. Okay, now, so what we want, so that's how to do the databases, and your homework for tonight is to write up some queries. And what I've done is I have augmented, did you see the instructions online? I have augmented it's not just Tom Fox. There's a bunch of other families with various employment statuses and various numbers of children and all kinds of stuff. So you have that to test your queries with. And then what I want you to do is put the queries in the documentation section. And then I'll copy, this one's going to be harder for me to grade. I'm going to have to copy and paste the queries and actually, do it by hand, manually. But anyway, just follow those directions. That'll be good. Okay, now, what we're going to do is, let's take a look at a finite state machine. Now, you guys, so who here, let me say it again. Who here has not ever seen the concept of a finite state machine before? Some of you guys have never seen, you don't know what a finite state machine is? Yeah, see, the people who are not in computer systems, might not know what a finite state machine is. But it's really not very difficult. It's kind of neat. And I've got, a few figures to go through here for those of you who haven't been exposed to this yet. But I think you'll see what it is. Now, look, you guys. Oh, by the way, this figure 7.10 is from a book that I wrote that you're going to be using in computer systems. But this is all on the slides online. Now, so check it out. This is an example of a finite state machine. This right here, figure 7.10, is an example of a finite state machine. Now, for those of you who know what a finite state machine is, why is this called a finite state machine? Because what are the states? How many states does this machine have? 3. What is the label of the states? The states are labeled what? A, B, and C. So there are 3. Is 3 finite? Yeah. 3 is a finite number. So therefore, this is a machine with a finite number of states. That's why it's called a finite state machine. Are you with me? Now, so states are the circles, right? That's one part of a finite state machine. Now, one of the states is called the start state. Can you tell from this figure, just sort of intuitively, which state is the start state.
Okay.
And how did you know that? Because it says start with an arrow into A. Okay? Is everybody good with that? So that's the start state. Now, what do we have in between each state? We have a what? An arrow. And what are these, for those of you guys who know finite state machines, what are those arrows called? They're called what? Starts with a T. Just a little vocab here. Transitions. They are transitions. Okay? So the way you look at this is you say you can make a transition from state A to state B on a letter, because this letter is the labels the transition from A to B. Does everybody see that? And furthermore, if you're in state A and you have a digit, then you can go from state A to state C on a digit. We'll see what this means in a minute. And similarly, if you're in state B, you can go from state B to state B on a letter. And if you're in state B, you can go from state B to state B on a digit. And if you're in state C, you can go from state C to state C on a letter, or you can go from state C to state C on a digit. Is everybody with me on that? Now, look, you guys, what we have, what this one more thing, one more item of a finite state machine. One or more of these states has a double circle. Do you guys who know about finite state machines, what is it called? What is the state called that has a double circle around it? That is a what state? You remember what those are called? Those are called final states. Yeah? Now, and so which state, just to identify it, which state up here is the final state? It's B, state B, right? Now watch this, you guys. What this finite state machine does is it recognizes certain strings. Okay, it recognizes certain strings. And we have here on the slide an example of the string CAB3. Let's look at it here. CAB3. Now what you have to do is you have to kind of like imagine that there is a little marker and you're starting at the start of the string. So here's the marker, right? And you start here. You start here. And then you imagine this. Here's what you imagine happening. You imagine the starting here, and so I'm putting my finger here on this little cursor right here, right in front of the C. And then you imagine that there's a little train or a ladybug or something. Imagine a ladybug, okay, starting at the start state, which is A. Now watch this. When I scan this input and go from here, and I go from here to here, what have I scanned? What have we scanned? And we go from here to here. We have scanned C, which is a what? Is it a letter or is it a digit? It's a letter. So I'm going from here to here, we scan a letter. That means that over here, what do? We go from what to what? We go from A to B, because we can only go from A to B on a letter. Now do you see the correspondence between this and that? How that works? All right, A to B. And now what's the next thing we're going to scan here? A, which is a letter. So what does that mean we're going to do on B? We're in B now, right? The ladybug's in B. So now what do? We go from B to B on a letter. And then what do? B. And then what happens? B to B on a letter. And then what? Digit. And so B to B on a digit. Now we're done with our string. And the question is, what state are we in? We're in state B. But what kind of state is B? B is a final state. Therefore, this string is a good one. It passed the test. Are you with me? What kind of a string would pass a test? Can you tell by that which kind of a string would pass, would pass the test? Can you give me another example of a string that would pass the test? One that starts with a letter. In fact, one that would not pass the test would be what? One that starts with a digit is right. So what does this recognize? This recognizes identifiers that start with a letter. Does that sound familiar? Isn't that a rule in C++ for writing an identifier? Identifiers can't start with digits.
I'm gonna try.
Oh, it wouldn't work because it would get confused with it being a number. You know, this is an identifier. You could have a variable named cab3 in C++. You can't have a variable named 3cab. If you try to do this with a variable, the compiler won't let you do it. So what happens is the compiler actually has little finite state machines in it to see what's legal and what's not. That's why it's useful. Uh-huh.
Does that mean that the compiler has to run a loop for every variable?
It does. It absolutely does. Yes. No, well, n, yeah, right. Well, you got n parameters to scan in the whole string, in the whole program. So yeah, that's exactly what it does. These finite state machines are running in the back every time you do, when you do a compile. Does everybody understand the rule? Because there is no more input and the last state is B, a final state, cab3 is a valid identifier. And here's another example. Look. Figure 7.14. This is a non-deterministic finite state machine to parse a signed integer. Now look. What's interesting about this one is that, which is the start state? A. Okay. And now let's suppose that we have the string is +203. Now, I mean, I don't have to put my finger here, right? Everybody sees the program. I mean, how it works. So here, so we're here. We get a plus. Can we go this way? Can we go this way? Well, not the minus. Can we go this way? No. We would go plus, right? Okay. So we go plus here. Whoosh, that takes us to B. Are you with me? Now, what's the next thing that we scan? The 2, which is a digit. Now, do you see a problem? Yeah. Now we have a choice. When we're in state B and we have a digit, we could either go up or we could go to itself. Well, look, you guys. What if we chose the wrong path and we went up? Then what would we be ready to scan next? A 0. But we're here and we have no transition on a digit. So it's a bzzz. Oh, it must not be a legal signed integer. But what's the problem? We tried the wrong one. So if we fail, oh, is this starting to sound familiar? If we fail, what do we want to do? Backtrack and try another one. Huh? So now we're back to here. We're back to here, and we scan the 2. Now this time let's scan the 0. So this time when we scan the 0, let's stay at B. Are you with me? Then what happened? And so now we're at B, and now we're ready to scan the what? The 3. But this time when we scan now suppose this time when we scan the 3, we stay here. Zoop. Now what's the problem? We're at the end and we're not in a final state. Bzz, fail. But we can do what? We can backtrack and do what? For the 3, go up to here, and boom, then we're home free. Finite state machine. Oh, that's a good question. Oh man, that's a really good question. The question is, what's the big theta? What's the efficiency of this? Log n doesn't enter into this because logs have to do with the depths of the tree. With where n is the number of characters? No, it's tricky. Yeah, it's weird. I can't say because it depends. And furthermore, non-deterministic finite state machines are less efficient than deterministic finite state machines. And guess what? It's actually, by the way, if any of you guys are slated to take the automata theory course, you will do this. You can prove that for every non-deterministic finite state machine, there is an equivalent deterministic finite state machine. And not only can you prove it, but you will actually be able to, you'll see the method by which you can do that. And then once it becomes deterministic, then it's big theta of what? N. Because every time you just do that scan, you know precisely which state to go to next. So there's actually a way to turn this into a deterministic finite state machine. But the neat thing about Prolog is, check this out, you guys. The neat thing about this is Prolog can handle this non-deterministically with backtracking. Almost no effort at all. This whole, this thing. Now watch how cool this is. Oh, rats. I need to do one more thing. Now, here is a non-deterministic finite state machine, but it's this epsilon is the empty transition. Now, why do you suppose we call it the empty transition? This epsilon is the empty transition.
Can take anything.
Well, what does it look like you can do?
Whatever's not there.
Yeah, what you can do is you can make the transition on the empty token and not scan anything. See, normally when you make a transition, you make a transition when you scan a letter. The empty transition says you can go to the next state and not scan. Are you with me? Do you see how that works? And do you see how this finite state machine will actually recognize 32, 32? It will start here, and it will make the empty transition here, not scan anything, and then scan, and you get the 3 here and the 2 here. See, but on the other hand, if it's hyphen 3, 2, then it will be hyphen and then 3 and then 2. And it will also get that
So
one.
in this particular example, having transitions for hyphen and for plus are irrelevant because...
Well, but this machine, they're not irrelevant in that this machine will recognize all these. This machine will recognize hyphen 3, 2, plus 3, 2, and 3, 2. This machine will recognize all of these. Each one of these is legal. But the way it recognizes this one is by taking that empty transition. So it's here, and then it takes the empty transition to state F, and then it scans the 3 to get to state
Well, because
M.
I was saying, because since they all go to the same state.
Oh, the fact that they all go to the same state is what? No?
Like how it's irrelevant to check the transitions, because since they all go to the same state anyways.
Well, no, hold on. What about this? What about 3 minus 2? This whole string. 3 would, okay, what would happen here? You take the empty transition to F, right? The 3 would get you to what? M, but now what? You have a minus, but there's no transition on M on a minus. So it will not recognize this string as a single signed integer. I don't know if that answered your question.
Yeah.
Kind of. Okay, so now, look at this. Our author, so here is from the, here, I think this is also from the 3rd edition. Yeah, you know what? He doesn't have a little arrow showing the start state, but his start state is S1. Okay? Now, can you tell from this finite state machine what kind of strings this thing recognizes? What are the, first of all, what are the letters that we're recognizing? A and B. So starting at the start state, any number of A's and B's, and what's the only way you can get to the final state? The only way you can get to the final state is through what? Is from what state?
S2.
Just S2. That means that the last letter must be a what? Must be a B. But what's the only way you can get to S2? Is with an A. And here you can have any number of A's and B's, right? And once you have an A and a B here, you can have any number of A's. But what do you know has to be, so what strings does this thing recognize? any string of A's and B's that does what? That terminates with, that has what? This will recognize that has AB at the end. Can you tell that from this? Can you analyze that from here? This will recognize any string that has AB at the end. So watch this. This is so slick. I think this is one of the best examples. This is one of the slickest. Okay, watch this. How are we going to look? So do you remember from that figure that the final state was S3? So we have a fact, final S3. Now watch this, final S3. Now what else do we have? We have a transition. Now what does trans mean? Transition from what to what? S1 to S1 on what? On A. We have a transition from S1 to S2 on A. Do you remember that from the figure? Okay, let's look at the figure briefly here. See, from S1 to S2 on A. Okay, and then we have a transition from S1 to S1 on B. That's that self loop, right? And then all the other transitions from S2 to B on S3, from S3 to B on S4. Okay, is that? And now what about that empty transition? Did we have some empty transitions? Oh, where it says null in his book, that corresponds to that epsilon. Okay, so what is that? He calls them null transitions. Okay, so where are the null transitions? From what to what? S3 to S1 and S2 to S4. But now we don't have any letters to do that. So we call that silent. S2 to S4, silent S3 to S1. All right? And now, you guys, what's really cool is this. Watch this. There is, if we say accepts, there are some rules for accepting. If we say accepts, if we start at S1 and our string is A, B, does this list end in AB? Does it end in AB? So guess what happens? It's true. It accepted it. Do you see what I mean? And if we say accepts, starting at S1, if we say accept starting, and this time if we say A, B, A, now what's going to happen? Yeah, because see what'll happen if we do A, B, A. There's no way we can end in the final state, right? So that's right. It'll be no. And not only that, if we say accepts, X, now, check, accepts starting at state S1. See, we always give the state that we're going to start at when we do the accepts query. Now if we say X1, which is a variable, X2, X3, check this out, this is so amazing. What do you suppose happens? In order for this to succeed, what do X1 and X2 and X3 have to be? A, B, or what? It has to be 3. And what's the other possibility? B, A, B, and then there are no more. Is that amazing? And the code, so here's what you have to, what now? Accepts, here's the code for accepts. Actually, well, I'll tell you what. Let's analyze this code at class next time. For tonight, all you have to do is write these facts. The final and the... I gave you a finite state machine. It's actually figure 717. It's all you have to do is just write those facts for this. Do you see how to do that? So it's just a plug and chug. I mean, there's no thinking involved. So just do this and get it to work, and we'll talk about how that accepts rule works tomorrow. That'll be in class tomorrow. But I think it's easy for you to do for your homework tonight. And include those accepts rules. Do include that so that it will work. All right, hold on, let me finish up. And so, see you all tomorrow.